This question teaches you how to find a present value of an annuity. Suppose that you have an outstanding loan that requires 10 annual payments of $2,300. Now is year 0 and the next payment on the loan is due next year. The last payment is due in year 10. There is a bank account that offers 5% annual interest rate. You would like to make a deposit into this account today, which would allow you to repay this loan. The first part of this question asks you to find the amount that you need to deposit. The second question asks you to demonstrate that the amount you deposited is indeed enough to repay this loan. Let's start with the first question. The amount you need to deposit is the present value of these payments discounted at 5%. To find the present value, we can use the annuity formula. Present value would equal to 2,300, which is our annual payment, divided by 5%, multiplied by 1 minus 1 divided by 1 plus 5% raised to the power of 10, because we have 10 payments. This would equal to $17,760. Let me demonstrate that if we discount annual payments by hand, we will get the same answer. Let me start with the first payment and find its present value. I will take the payment itself and I will divide it by 1 plus discount rate raised to power 1, because this payment occurs 1 year from now. If I extend this array all the way to year 10, this will give me the present value of each of these individual payments. For example, the very last cell gives me the present value of the last payment, $2,300, discounted to present. We're raising it to power 10 because this payment occurs in year 10. To find the total value of these payments in present value terms, we will just add them up. This gives us exactly $17,760, the same value that we obtained by using the annuity formula. Let's enter the second part of this question by demonstrating that depositing $17,760 is enough to fully repay this loan. We're beginning year 1 with this much money in our bank account. During this first year, the bank pays us 5% interest rate on this amount. So the interest that we earned would equal to the beginning balance multiplied by the interest rate of 5%. At the end of year 1, we're making our annual payment. And therefore, the end balance would equal to the beginning balance plus the interest that we earned minus the payment that we made. Then we're starting second year by having this much money in our bank account. During this year, we're still earning 5% interest on this balance, and we're making the same payment. And we're ending this year with the balance in our account of $14,865. Now, let's see what happens if we extend these arrays all the way to year 10. We will see that we will start year 10 by having $2,190 in our bank account. During this year, we're earning 5% interest on this beginning balance, which is exactly enough to pay $2,300 at the end of this year, which leaves us with the balance of exactly 0. We just demonstrated that depositing $17,760 now into a bank account that pays an annual interest rate of 5% is enough to repay this loan. Overall, what we learned in this question is how to find a present value of a stream of cash flows that represents an annuity. Suppose that you have an outstanding loan that requires 10 annual payments of $2,300. Now is year 0 and the next payment on the loan is due in year 6. The last payment is due in year 15. There is a bank account that offers 5% annual interest rate. You would like to make a deposit into this account today, which would allow you to repay this loan. What is the amount that you need to deposit? This question is similar to question 1 because we have the same annual payment, the same interest rate. The only difference is that our payments start in year 6 and end in year 15. So let's first find the present value of these payments by using brute force. So I'll start discounting each of these individual payments similar to what we did in question 1 by taking the payment and dividing it by 1 plus the discount rate, and I will raise it to the power which equals to the year in which this payment occurs. I will extend this array. This would give me the present value of each of these individual payments, and I will add them up, and this will give me the present value of all of these payments, which would equal to $13,915.42. Now let's do something smarter. First, I will relabel the timeline by denoting the first year in which we receive payment by year 1. In this case, year 6 in the actual timeline is year 1 in the new timeline. In this new timeline, the stream of payments looks like a regular annuity, and we can find its present value. In fact, we already found it in question 1. It equals to $17,760. But in the old timeline, this is the value in year 5, not present value. To find its present value, what we need to do, we need to discount it by dividing it by 1 plus our interest rate, 5%, raised to the power of 5. By doing so, we get $13,915.42. This is exactly the same answer as we obtained by discounting each payment manually. The stream of cash flows we studied in this question represents a delayed annuity. Now let's summarize what we learned in this question. If we need to find a present value of a delayed annuity that starts paying in year n, we need to do the following. First, we use the annuity formula to find its value in year n-1. And second, we discount year n-1 value to present. In this question, we will learn how to find present value of growing annuity. Now is year 0. A biotechnology company has developed a new nanorobotic surgical device. The patent on the device will last 15 years. You expect that the profit from the device will be $5 million in year 1. From year 1 until year 15, annual profit is expected to grow at a rate of 4% per year. After patent expires, the emergence of new devices and competition with other biotech firms will drive profits from the surgical device to 0. The question asks us, what is the present value of the new device if the discount rate is 9% per year? Let's first use brute force to find the present value of profits generated by this device. As question states, in year 1, this device generates $5 million in profits. From that point onwards, these profits grow at a 4% rate. So in year 2, the profit generated by this device will be 5 million multiplied by 1 plus the growth rate of 4%. And this growth will continue all the way to year 15. So in year 15, this device generates $8,658,382 in profits. Now, what I will do in the next column, I will discount each of these cash flows individually to present. So the present value of the first cash flow will be 5 million divided by 1 plus the discount rate of 9%. Raised to the power 1, this is the year when this cash flow occurs. And we'll continue doing so all the way to year 15. For example, in year 15, the present value of the profit that occurs in year 15 would be this value divided by 1 plus discount rate of 9% raised to the power of 15. Now what's left is to add them up. So the sum of these discounted values would represent the total present value of all profits generated by this nanorobotic device. Now let's do something smarter. Notice that the stream of cash flows that we have in this question represents a growing annuity. Each payment growth at a growth rate of G equals to 4%. The discount rate is 9%, and the number of periods over which we get cash flow is 15 years. So therefore, to find the present value of this stream of cash flows, we can use growing annuity formula. So the present value of this growing annuity would be the first payment, which is $5 million, divided by discount rate 9% minus growth rate 4%, multiplied by 1 minus 1 plus G, which is 4%, raised to the power of 15. This is the total number of periods over which we receive the cash flow, divided by 1 plus discount rate 9%, raised again to the power 15. So this value, if we compute it, would equal to $50,557,250. Exactly the same value that we obtained by applying the brute force. Overall, it is much more efficient to find the present value of this stream of cash flows by using the growing annuity formula instead of discounting each of the individual cash flows by hand. And therefore, this should be our preferred approach going forward. In this question, we will learn how to work with regular and delayed perpetuities. Suppose that you are chief financial officer of a company that owns a commercial real estate property that is currently unused and is unoccupied. Assuming that the appropriate discount rate is 7%, you would like to estimate the value of this property under the following two assumptions. A. You can start renting it out immediately. You expect the annual rental profit to be $650,000 and to continue in perpetuity. The first payment will occur in year 1. B. You will spend the first 4 years redeveloping this property. The present value of redevelopment costs is $1 million. Starting in year 5, you will receive annual rental profit of $950,000, which will continue in perpetuity. What is the value of the property under scenarios A and B? Let's start our analysis by looking at scenario A. If we rent out our property immediately, we will receive $650,000 in year 1. This profit will continue being generated every year in perpetuity. So therefore, this stream of cash flows represents a regular perpetuity. The first payment starts in year 1 and it continues forever. Therefore, we can find the present value of this perpetual stream of cash flows by taking the first payment that we receive of $650,000 and just dividing it by the discount rate. In our case, it is 7%. So the present value of this rental profit is $9,285,714. So therefore, this property will generate exactly that much throughout its perpetual lifetime. Now, let's turn to the analysis of scenario B. In this scenario, we redevelop the property during the first 4 years. It starts generating a profit of $950,000 in year 5, and this profit will be generated every year thereafter forever. We call this stream of cash flows a delayed perpetuity. It is similar to a regular perpetuity, with the only difference that the first cash flow starts not in year 1, but later. In our case, it starts in year 5. To find the present value of the delayed perpetuity, let's follow an approach we developed in question 2. Let's draw a timeline a new timeline by denoting the first year in which we receive payment by year 1. In this case, year 5 in the actual timeline is year 1 in the new timeline. In this new timeline, the stream of payments looks like a regular perpetuity, and we can find its present value. It equals to $950,000 divided by 7%, which is $13,571,429. Importantly, note that in the actual timeline, this value is in year 4, not in year 0. To find its present value, we need to discount it further by dividing it by 1 plus 7% raised to the power of 4. Therefore, the present value of this delayed perpetuity is $10,353,578. Overall, what we found so far is that this property generates $10,353,578. Taking into account the present value of redevelopment costs, which are $1 million, the value of the property under this scenario is $9,353,578. Recall that if we choose scenario A, the present value of the property is $9,285,714, which is less than what we got under scenario B. The conclusion is that we should redevelop this property because this would generate higher wealth as indicated by the larger present value. Jeff Bezos recently made an announcement that he would donate $10 billion to combat climate change. Suppose that he plans to establish a foundation to which he will pledge the entire amount of $10 billion. Every year, his foundation will distribute funds to organizations that fight climate change. Let's assume that the foundation will invest funds into financial assets that will on average generate nominal annual rate of return of 8%. Now, the first question is asking us, if Bezos Foundation wants to be able to distribute funds in perpetuity, and if they plan to distribute the same dollar amount each year, what will be the annual distribution amount? Now, we will assume that the first distribution happens in exactly 1 year from now. Notice that the distribution stream from the foundation represents perpetuity. Suppose that the annual distribution equals to C dollars. Then the present value of this stream of payments can be written as present value equals to C divided by 1 plus R plus C divided by 1 plus R squared plus C divided by 1 plus R cubed, and so forth. Remember, this is a perpetuity, so this is an infinite stream of cash flow. We have learned in the lecture that the present value of such perpetuity equals to C divided by R. Now, the question gives us the present value of this perpetuity. This is the amount of money that Jeff Bezos pledged to the foundation, which is $10 billion. Now, given the interest rate of 8%, we can solve this equation for the annual payment amount, which would be C equals present value multiplied by interest rate R, or in this case, $10 billion multiplied by 8%, which would equal to $800 million. Let's start by assuming that the annual distribution amount equals to C, similar to what we did in part A of this question. Then we can write down the present value of the stream of distributions from Jeff Bezos Foundation. It's going to equal to C, this is the current distribution, plus C divided by 1 plus R, this is the present value of the second distribution, which will happen 1 year from today, plus C divided by 1 plus R squared, this is the present value of the third distribution, which will happen 2 years from now, plus c divided by 1 plus r raised to the power of 3, which is the present value of the fourth distribution, which will happen 3 years from now, and so forth. Now, we need to find the present value of this amount on the right-hand side of this equation. To do this, notice that this part of the equation is just the regular perpetuity. And we already know the present value of the regular perpetuity. Therefore, we can write down this equation as such. So the present value of this stream of cash flows equals to C plus C divided by R. Now, we know that the present value of the pledged amount to the foundation is $10 billion. Given that the interest rate is 8%, we can solve this equation for the annual payment amount. So the annual payment amount C would equal to the present value divided by 1 plus 1 divided by R. Plugging in the numbers, 10 billion and 8% interest rate, we get 740,000 and $740. Therefore, the annual distribution amount will be around $741 million. Note that if Jeff Bezos starts distributing funds in 1 year from now, the annual perpetual distribution amount will be $800 million. If, on the other hand, he starts distributing money immediately, this lowers the annual perpetual distribution amount to $741 million. This does make economic sense due to the fact that the immediate distribution lowers the balance of funds on the foundation's balance sheet and therefore lowers its ability to earn 8% annual interest rate on this amount. Now suppose that the expected future annual rate of inflation is 2%. If Jeff Bezos wants to distribute an equal annual amount in today's dollars to guarantee purchasing power of distributed funds, how much would the annual distribution amount be? Assume that the first distribution happens 1 year from now. Suppose that the annual distribution from the fund equals C dollars. Let's denote by I the annual rate of inflation. Future distributions from the fund need to grow at the same rate as the inflation to guarantee their purchasing power. In year 1, for example, distribution should equal to C times 1 plus I. More generally, in year T, distribution amount would equal C times 1 plus I raised to the power T. For example, in year 2, distribution amount will be C times 1 plus I raised to the power 2. Let's put these distributions on the timeline. For comparison, let's also draw a stream of payments that represent a regular growing perpetuity. Notice that the two streams look alike with one difference. For regular perpetuity, the first payment in year 1 is C, and the second payment in year 2 is C times 1 plus G, where G is the growth rate. In our case, however, the first payment is C times 1 plus I, and the second payment is C times 1 plus I squared. Now, mathematically, we can make our stream of payments look like a regular perpetuity if we factor 1 plus the rate of inflation term out. To see this, let's write down the present value of our stream, which is present value equals to C times 1 plus I divided by 1 plus R plus C multiplied by 1 plus I squared divided by 1 plus R squared, and so forth. Factoring 1 plus I out gives us the following expression. Present value equals to 1 plus I multiplied by C divided by 1 plus R plus C multiplied by 1 plus I divided by 1 plus R squared, and so forth. The expression inside large brackets looks just like a regular perpetuity. Hence, its present value is just c divided by r minus I, and therefore the present value of our stream is 1 plus I multiplied by c divided by r minus I. All that's left here is to find c in this expression. Remember that we're given the present value, which is the amount that Jeff Bezos pledged to the foundation, which is $10 billion. Given the interest rates of 8%, we can solve this equation for payment amount C. 10 equals to 1 plus 2%, which is the rate of inflation, multiplied by C, divided by 8%, which is our interest rate, minus 2%, which is the rate of inflation. Rearranging, this gives us C equals to 10 times 8 minus 2%, divided by 1 plus 2%. This equals to 588,235,294, or roughly $588.2 million. Note that the value of $588 million that we found in this question is significantly lower than the constant distribution value that we found in part A, which was 800 million. Intuitively, since we have to adjust for inflation, we have to start paying lower amount so that we have enough funds to guarantee all the future payments and adjustments for inflation. In this question, we will learn how to work with effective annual rates and with annual percentage rates. Let's start with part A of this question. A credit card company charges you 20% annual percentage rate, or APR, compounded monthly. What is the effective annual rate, or EAR, that you are being charged? To find the effective annual rate, we use the formula we developed in the lecture. EAR equals to 1 plus APR divided by K, and raised to the power K, minus 1, where K is the number of compounding intervals in a year. In our case, APR equals to 20% and K equals to 12 because the credit card company compounds interest monthly, and there are 12 months in a year. This gives us EAR of 21.94%. Overall, this results indicates that the bank effectively charges us 21.94%, which is substantially higher compared to the APR of 20%. Let's continue with part B of this question. Suppose that you work for a credit card company and you would like to earn an effective annual rate of 25% on your credit card loans. You are free to choose a compounding interval with the only constraint that the shortest period has to be 1 day. Assuming that you want to present the lowest APR to your customers, what is the optimal frequency of compounding? What is the APR at the optimal compounding frequency? As we have seen in the lecture, for a given APR, the higher the frequency of compounding, the higher is the effective annual rate. Our goal in this question is to find the optimal compounding frequency for a given EAR that would result in the lowest APR. Intuitively, for a fixed EAR, we should compound interest as frequently as possible because the higher compounding frequency will lead to lower APR. In our case, the optimal frequency of compounding should be daily. Let's do the following. First, we will compute APR assuming daily compounding. Then we will compute APR assuming quarterly compounding. And then we will generalize this result. Let's start with daily compounding. Assume that there are 365 days in a year. For a given effective annual rate of 25%, let's find APR. Let's start with the basic relationship between EAR and APR. 1 plus effective annual rate equals to 1 plus APR divided by K, which is the compounding frequency, raised to the power K. We can rearrange this equation to find APR as a function of EAR. APR would equal to K, the compounding frequency, multiplied by 1 plus EAR raised to the power 1 over K minus 1. For an effective annual rate of 25% and daily compounded interest, APR in this case would be 22.3%. Now, let's compute APR if interest is compounded quarterly instead of daily. In this case, compounding frequency K would equal to 4, which would give us an APR of 22.9%. Therefore, if we choose quarterly compounding, the APR of 22.9% would give us effective annual rate of 25%. But if we choose daily compounding, the APR of 22.3% would still give us the effective annual rate of 25%. So given that we want to earn effective annual rate of 25%, and we want to display the lowest APR to our customers possible, we should choose daily compounding. This would allow us to advertise APR of 22.3%. Let's generalize this result. Here, I have created an array that denotes the frequency of compounding from 1 all the way to 365. 1 corresponds to annual compounding, and 365 corresponds to daily compounding. Now, for each of these intervals, I will compute APR. We see that for quarterly compounding, APR equals to 22.9%, which matches the number we found before. For annual compounding, when K equals to 1, APR is 25%, which intuitively should be correct because when interest is compounded annually, APR should equal to EAR. Now, the plot to the right shows APR as a function of compounding interval for a given effective annual rate of 25%. This is a decreasing function, which indicates that highest compounding frequency corresponds to lowest APR. Recall that for daily compounding interest, APR equals to 22.3%. Overall, this illustrates that our decision to go with daily compounding is the right one. Let us start solving this question by first computing monthly interest rates on the old and the new loan. Recall that on the old loan, we're paying 6.5% effective annual rate. To find the monthly rate, let's start with the following equation. So 1 plus effective annual rate would equal to 1 plus monthly rate raised to the power 12. From this equation, we can find monthly rate by just inverting it. So it's going to be 1 plus effective annual rate raised to the power 1 over 12 minus 1. So it's going to be 1 plus 6% raised to the power 1 over 12 minus 1. And this would give me 0.487%. So this is the monthly rate that we're paying on the old loan. To find the monthly interest rate on the new loan, note that the new loan is quoted to us as annual percentage rate, monthly compounded. So therefore, for us to find the monthly rate, all we have to do is we're taking this monthly compounded APR and we're dividing it by 12, which is 4.5% divided by 12. This would be 0.375%. So this is the monthly interest on the new loan, and up here was the monthly interest rate that we're paying on the old loan. So you could already see that we got a better deal on the new loan, so therefore refinancing the old mortgage with the new mortgage would lower our monthly payments. Now let's find monthly payments on the old and the new loan and compare them. First, let's start with the old loan. So the current value, the present value of the mortgage that we have is $300,000. So this must equal to the monthly payment that we're making, and I will denote it as CO, as the monthly payment on the old mortgage, divided by RM. So this would be the rate, the monthly rate on the old mortgage, multiplied by 1 minus 1 divided by 1 plus RM, raised to the power 240. 240 because we have 20 years left on the life of this mortgage. And so for us to find our monthly payment, all we have to do, we have to invert this equation. So it's going to be $300,000, and then we'll divide it by 1 divided by RM, 1 minus 1 divided by 1 plus RM, raised to the power 240. If we solve this equation by plugging in the interest rate of 0.487%, the monthly interest rate, we will get CO, which is the, again, monthly payment on the old mortgage, of $2,121.88. Now let's do the same for the new loan. So I can write down the same equation. So it's the same if we were to refinance right now. We need to still raise the present value of $300,000 so that the proceeds from the new loan can be used to repay the old loan. And that again would be equal to our monthly payment, and I will denote it as CN to denote the new payment on the new loan, divided by RM, 1 minus 1 plus RM, also raised to the power 240. So now this RM is the interest rate on the new loan, and I can find CN similarly by just inverting this equation. So CN is going to equal to $300,000 divided by 1 divided by RM, 1 minus 1 plus 1 RM raised to the power 240. And so if we compute, if we plug in RM that equals to 0.375%, we're going to get the monthly payment on this loan of $1,897.95. Now we can see that by refinancing the old loan with the new loan, we're saving the difference between these two amounts, what we used to pay on the old loan and our new lower monthly payments. The difference is about $223.93. So this is by how much we are lowering our monthly payment on the mortgage. Now let's do cash out refinance. So instead of lowering our monthly mortgage payments, we will continue paying the same amount as we paid before, but because this new mortgage is cheaper, we will be able to borrow a larger amount from a bank and pay the existing loan and use the remaining cash for other purposes, such as the question states, buying a new car or doing something else. So the question is, given this new cheaper rate, how much we can borrow if we were to continue paying the same amount that we paid before on our old mortgage? So the answer is simply this. So this question is asking us to find the present value of our old payment. Recall that our old payment was $2,121.88 at the new monthly rate, which was 0.375%. So 375. I'm just using the annuity formula to find the present value of this amount. 1 minus 1 divided by 1 plus this interest rate, raised to the power 240. Recall that this is a 20-year loan on which we're paying monthly payments, so there are 240 months. And by computing this amounts, this is the present value of how much we'll be able to borrow. This gives me $395.29. We will take this new loan from the bank and pay $300,000 in our existing mortgage to the other bank, therefore leaving ourselves with $35,395.29.